Swayam Prabha. Digital India. Educated India.
Now we are going to talk about what is called minimization algorithms. Before I start talking about it, I want to give you a preamble. The least square solution is expressed as the minimum of a cost functional that we concocted, which is the sum of the squared residuals. One way would be to apply the rules of calculus to define the minimizer. The minimizing point is also called minimizer, to express the minimizer as a solution of the gradient equation, and at that solution the second derivative must be positive definite. So, we derived explicit expressions for the minimizer, and that led to the method of normal equation, that further led to our seeking solutions to solving linear systems. That is one way. Another way is minimization technique. This minimization technique is induced by our analysis of how people climb mountains. It is called hill climbing. Several people have reached the top of Mount Everest. So, how do they do? They start from one base station, they survey the local land, they know where Everest is located, they can't trek for more than, let us say, 6 hours a day because they have to carry a lot of stuff in their back. So, now they make a calculation like this: if I trek 6 hours, in which direction should I move in order to be able to maximize the increase in height? So, I go to the next base station. So, what is the idea here? A hill climber moves from base station to base station to base station. They are greedy. They would like to be able to reach the top quickly. So, every day when they trek, they would like to be able to increase their elevation. So, they generally use a greedy strategy after doing a survey of the local terrain and decide the direction in which they need to trek. So, this is for maximization. We are interested in minimization. So, maximization and minimization are related to each other. Instead of going up the hill, I am going to come down the valley. So, what are the basic steps we have to ask? Wherever we are, that is the base station, our current location. Which direction should I move? How far should I move in that direction? And then go from the original point to that point. Then redo the same thing at the new point, namely decide the new direction in which you have to move and how far you need to go. This is called iterative minimization. I do not want you to confuse this iterative minimization with the iterative methods for solving linear system. That is an iterative method, this is an iterative methods. Iterative methods are sequential. You remember, I have already introduced you to an iterative, sequential, recursive. All these words are used rather synonymously about on the topic of modeling sequential estimation in the context of least squares as observation come in. So, you have already been introduced to sequential methods. The sequential methods for solving matrix problem I am not covering, but I am now coming to cover a new class of sequential minimization that directly minimizes the objective function without having to compute the derivative. So, what is the idea? Which one you use? If you knew the function and if you can compute the derivative, one way would be to compute the derivative equal to 0 and solve it. Another possibility, another alternate thing is, suppose your cost function you don't know explicitly, but it's a black box. If you give an input x, it will give you the value of the output f of x. In such cases, you may or may not be able to calculate the derivative. Sometimes you may know the functional value, you can compute the derivative, yet I may not be wanting to equate the derivative 0 to compute the minimizer. I want to use the derivative information to decide which direction do I move. So, the derivative can be used in two different ways, one by equating to 0 and reducing to one of solving a linear equation. Another one would be use the derivative to decide which direction to move and how far we move. It is this latter technique we are going to be talking about this, and there are again tons of software available. Now, I am going to give you a basic idea, minimization problem in 1D. We have already introduced the notion of a convex function when we were talking about multivariate function, basic ideas of optimization. Why do we assume a function, a scalar valued function of a scalar is a convex function? That means the minimum exists and is unique. So, here is an example of a convex function, which is a quadratic function ax square plus bx plus c. I am assuming the coefficient a is greater than 0. If a is greater than 0, this must be a quadratic function with a minimum. We all know the behavior of quadratic functions. So, how are we going to understand and find where the minimum is? I am using the notion of what is called perfecting a square. So, I can add and subtract terms to be able to express this function as a sum of a perfect square and a correction term. To perfect the square, I need to add. So, whatever I add, I am subtracting. So, this function I want you to be able to check is a homework problem. This is a very simple homework problem. The method is called method of perfecting the square. So, let us look at the first. If a is positive, this is positive. The second term is square, that is also positive. The next term, b square minus 4ac by 4a, it could be positive or negative, but it is independent of x. I have to optimize with respect to x. So, this term is a constant term, and we already know constant term does not affect the location of the minimizer. Therefore, when will this function be minimum? This function will be a minimum when x is equal to minus b by 2a. That comes from here. So, I can't eradicate the second term, that is a constant. The first term is positive term. To minimize means I should reduce the positive term. What is the minimum value a positive term can take? 0. So, a cannot be 0. So, x plus b by 2a must be 0. So, if I set x star is equal to minus b by 2a, I get the minimum value. So, that is the minimizer. So, this is the minimizer. The minimum value f of x star. So, there are two things, the location where the minimum occurs and the value of the function at the minimum. So, this is the value of the function of the minimum. F of x is a parabola, it intersects the x axis at 2 points, minus b plus or minus square root of b square minus 4ac by 2a, only if b square is greater than 4ac, and otherwise if b square is not greater than 4ac, the function is always above the x axis. I am now going to illustrate this by an example for those of you who I want to reinforce this intuition. So, f of x is equal to x square plus x plus 1, a is 1, b is 1, c is 1. I can express this as x plus half whole square plus 3 by 4. The minimizer is minus half, the value of the minimum is 3 by 4. In this case, b square is less than 4ac. So, the two roots are complex. The two roots are complex. I am working in the real plane, so there is no zero crossing along the x axis. The function lies above the x axis. So, that is an example, and this is the minimizer. The minimum occurs at minus half. Now, I would like to be able to generalize. So, this is a little picture using 1D. Please understand, we always get a geometric intuition by working problems in a low dimensional space and extend it to high dimensional spaces, and that is what we are going to use. So, f of n is from Rn to R, is a convex function in Rn. I do not want to repeat the definition of convexity, we have already seen that. A typical convex function is again a quadratic function. This is 1/2 of x transpose Ax minus b transpose x plus c. A is an SPD matrix. If I compute the gradient of this is Ax minus b. If I set the gradient to 0, that is equal to Ax is equal to b, so x star is equal to A inverse b. So, the minimizer of this quadratic function is A inverse b. If I now substitute x star is equal to A inverse b in this and simplify, I get the minimum value of f of x star is equal to 2c minus b transpose A inverse b by 2. That is the minimum value of f of x. I would like you to be able to check everything. That is again a homework problem. Please check this. So, what is it now we want to do? Instead of solving Ax is equal to b, we want to be able to minimize f of x indirectly using the gradient information. So, there are two things. You compute the gradient in both the methods. In one method, you equate it to 0 and solve the resulting equation to find the minimizer. That is what we did so far. Now, I am not going to equate it to 0, I am going to use the gradient itself. The gradient is going to be guiding me in my search for a minimum. So, that is the idea. Now, how am I going to use the gradient? I am interested in the minimization. Minimization algorithms are called descent algorithm because I am going to be descending into a valley. Maximization algorithms are called ascent algorithm or hill climbing algorithm. Please understand, we are designing this algorithm based on the human behavior. Sometime in algorithm analysis, we talked about nature induced algorithms. There is nothing more nature induced algorithm than mimicking what humans do when they want to climb mountains. So, this is a very interesting application of trying to capture the human behavior. At any point x belonging to Rn, what is the basic idea? The gradient of a function denotes the direction of maximum rate of change. The gradient of a function denotes the direction of maximum rate of increase. So, if you go along a gradient, you can make the function value increase. So, if you go along the direction opposite to the gradient, negative of the gradient, you can decrease. We are interested in decreasing instead of increasing. So, here is the picture. So, there is a contour of the function f of x equal to c. So, I am given a function f of x. I am going to draw the contours. What is the contour? It is the locus of all the points such that f of x takes a constant value. So, let us assume that that locus is given by this curve. I am considering a point on that locus x. If I compute the gradient tells you the direction of maximum increase, the negative of the gradient tells you the direction of maximum decrease. And this is the tangent at the point x. The gradient at a point is always perpendicular to the tangent to the contour at the point x. These are the simple geometric facts. These are the simple geometric facts I'm going to use. So, what are the various things I need? F of x, set f of x is equal to constant. I look for the contours of f of x is equal to constant, which is the locus of f of x, for which the value of f of x is equal to c. You pick a point x on the locus, you compute the gradient, you compute the negative of the gradient. The gradient represents the maximum rate of increase, negative of the gradient represents the maximum rate of decrease. I have a tangent, and the tangent and the gradient are mutually orthogonal to each other. Now, let us consider a direction p as shown in the figure. P is a direction that makes an acute angle theta, the acute angle theta with the negative of the gradient. Please understand, this is the negative of the gradient, P is the direction. So, if I took the inner product of P transpose the gradient, please understand, if this theta, if this angle theta is less than this angle is greater than 90 degrees, is greater than 90 degrees, and we all know from basic inner product, the inner product of P transpose del f with the gradient of f is equal to the gradient, the 2 norm of that, the 2 norm of f of x times cosine of theta. If the theta is greater than 90 degrees, cosine is negative. Therefore, the inner product of P transpose or gradient of x is less than 0. So, if there is a direction P for which this property, namely the inner product of P with respect to the gradient is negative, that means that is a descent direction. That is a descent direction. Why is this called a descent direction? By going along P, I can hope to decrease the value of the function. And what is another way of looking at P? P is a descent direction if and only if it makes an angle theta with respect to the negative of the gradient, which is less than 90 degrees, So, I can look at P with respect to gradient, or I can P look with respect to the negative of the gradient. Because it is making an angle less than 90 with respect to the negative of the gradient, and if my negative of the gradient is called the descent direction, is a direction of maximum rate of decrease, by going along P, I can hope to decrease the value of the function, and that is the role of what is called a current operating point x, a descent direction P at the point x. So, now I would like to be able to introduce the notion of what is called steepest descent direction. Why steepest? Please understand, I would like to get maximum benefit. What is the maximum benefit? A hill climber wants to get the maximum increase in level. A minimizer wants to get the maximum decrease in the depth. I want to be able to come down by a largest amount. So, I am going to pick a real number alpha greater than 0. I am going to express f in the form of a Taylor series at the point x along the direction P, where alpha is called the step length. So, x is a n vector, P is a n vector, alpha is a constant. So, if this is the point x, if this is the direction, this is the point x plus alpha p. When alpha is not large, x plus alpha p is a point along the direction p, but close to f of x, close to x. So, if alpha p is not too large, I can approximate the value of f of x plus alpha p by a first order Taylor series, f of x plus alpha times p transpose gradient of f of x. Now, if p is a descent direction, p transpose gradient of delta f of x must be 0. So, I am subtracting a quantity from f of x to get this. Therefore, f of x plus alpha must be strictly less than f of x, since p is a descent direction. That means, by going along P chosen the way that we have, I can hope to decrease the value of the function. Once I know I can decrease the value of the function, we get greedy. I would like to be able to decrease the value of the function by a maximum amount. When will this be maximum? Please understand, here is the inner product. Inner product of two vectors is maximum only when the angle between the two vectors is 0. I hope you are all with me now. A transpose B is norm of A times norm of B times cosine of the angle theta. A and B are fixed. What is changing? Theta. When is theta maximum? When theta is 0. So, only when A and B align themselves along the same direction, that means when they are collinear. So, that is the result we come from vector algebra. So, by picking P is equal to minus the gradient, please understand, P is equal to minus the gradient, I get what is called the steepest descent direction. So, descent, steepest descent. So, I have satisfied my greedy nature to get the maximum benefit out of going along the direction. Instead of P, choose P be equal to minus the gradient. So, if p is equal to minus gradient, this term is square of the gradient, square of the norm of the gradient, that is maximum. So, I am trying to decrease the value by a maximum amount, alpha is positive and this is strictly less than f of x. So, we get the maximum rate of decrease of f of x at x. Now, please remember, in the case of least squares, we introduced the notion of a residual vector to measure the difference between the left hand side and the right hand side. Here also I am going to use the residual vector, slightly different role, but residual is residual. Residual is residual. So, when Ax is equal to b, I am sorry, when, let me go back, when z is equal to h of x, we call the residual r to be z minus h of x. When Ax is equal to b, please understand, for the quadratic function, the minimum is attained at Ax is equal to b. So, when x is equal to x star, at the minimum Ax must be equal to b. If it is not, Ax is not equal to b, I have to measure the difference by a residual. So, in this case, how am I defining a residual? B minus Ax. So, this one and this one are analogous. I use the residual in least squares in one way, I am going to use the residual in another way in the sequential minimization technique. So, if I am at the current operating point, b minus Ax is called the residual. B minus Ax, now please understand, the gradient of this function is Ax minus b. So, b minus Ax is the negative of the gradient. So, the residual has the automatic meaning of, or automatic interpretation of, the negative gradient, which is the steepest descent direction. So, in the case of least squares, the residual told you the difference between the left hand side and the right hand side. In this case, the residual tells you how far we are away from the minimum, and residual tells you also the direction of the steepest descent direction. So, residual has a dual role in here. The residual is the steepest descent direction at of f of x at xk. When residual is 0, x star xk is equal to x star is equal to A inverse b. So, because of this, I can use the norm of the residual as a measure of how far I am away from the minimum. Now, please understand, this is the interesting thing. I do not know where the minimum is. So, but I can have a measure of how far I am away from the minimum by looking at the residual. I hope you are with me. This is a very interesting mathematical fact. I do not know where x star is. At x star, the residual must be 0. At any other point, the residual will not be 0. So, the residual being not 0 is an indicator that I am not at my promised land. Therefore, the residual, the norm of the residual can be used to test convergence of the iterative minimization. Look at that now. We are trying to use the residual cleverly to play many different roles. Residual tells you the negative of the gradient, steepest descent. The magnitude or the norm of the residual vector tells you, can be used to test how far I am away from that and use it to design algorithms to get good stopping criteria. These are all important parts of development of algorithms. So, what am I doing? I could have easily given you the algorithm and then say, hey, go and program, but I am trying to derive the algorithm. So, there are two ways. One is to give you the algorithm without telling how the algorithm is designed. Another way is to be able to design the algorithm itself from ground up. I always prefer the latter approach. I always derive the algorithms, and that's our philosophy. Look at that: LU decomposition, Cholesky decomposition, QR decomposition, SV decomposition, SVD, the singular value decomposition. We have not simply given the algorithm; we have actually derived everything from the basics. So, I am trying to continue the same way. So, now given all this preparatory work, I am now going to give you the framework for steepest descent algorithm. Steepest descent algorithm is a methodology by which I can iteratively minimize a cost functional. I am trying to illustrate this iterative minimization using a quadratic function. Please understand, I need a problem. So, in the minimization problem, the minimizing the quadratic function with symmetric positive definite matrix is called the model problem. The model is not used in the sense of modeling data. It's a model problem. It's a standard problem. For example, I will give you an analogy of some ideas. When you want to learn piano, what is the first lesson you do? Twinkle, twinkle, little star. So, to learn piano, you need to learn to play Twinkle, Twinkle, Little Star. If you want to play minimization, the Twinkle, Twinkle, Little Star for minimization is a quadratic function. That's the analogy. So, I am trying to illustrate the concepts behind the design of minimization algorithm using a model problem called, this is not model problem. Model problem called quadratic minimization. What is the quadratic minimization problem? Once again, 1/2 of x transpose Ax minus b transpose x plus c, where A is a symmetric positive definite matrix. So, to summarize how we got here, we talked about hill climbing, we talked about steepest descent, we talked about steep descent direction, negative the gradient being in the steepest different direction. We showed I can get the maximum decrease by going along the negative of the gradient. So, negative of the gradient is in fact the residual. So, residual is a measure of how far I am away from the minimum. At the minimum, residual is 0. So, I am going to use residual not only to use to find the next such direction, but also to decide how far I need to go to be able to say I am converged. So, the multiple role played by the residual. So, let us assume I am at an intermediate stage xk. I want to be able to go to xk plus 1. This is like a hill climber. I am at the base station xk. I want to go to the base station xk plus 1. I am going to go in the direction rk. Rk is the negative of the gradient. Alpha essentially tells the distance by which I am going to move along. So, along rk. So, this is xk, this is rk, this is the point xk plus 1, which is equal to xk plus alpha rk. Alpha times rk is a segment of the vector. I am going to add a segment of the vector to the vector xk to get the new point. I already know rk. I want to be able to settle what is best alpha, how far I need to go. So, what are the conditions in here? I already know f of xk plus 1 must be less than f of xk. That means I am assured that the function is going to decrease. But the amount of decrease, the value of f of xk plus 1 minus f of xk, please understand f of xk is a scalar, f of xk plus 1 is a scalar, the difference are 2, the absolute value. The absolute value of the difference, it depends on alpha, because I know rk, I know xk, the only unknown is alpha. Alpha is called the step length parameter. So, at xk, the direction of search is rk, that is fixed. Given xk and rk, how to choose alpha such that we get the maximum decrease in f of x as we move from xk to xk plus alpha rk. So, the whole problem of minimizing f of x in the whole space now reduced to the problem of minimizing f of x along the direction rk. So, this is called the resulting 1D minimization problem. In algorithm analysis, this is called divide and conquer. So, I am trying to divide an n-dimensional problem to a sequence of one-dimensional problem. The sequence of one-dimensional problem we know how to solve. Why? That is the problem I started with. You may remember the opening couple of slides of this module dealt with minimizing 1D functions. So, with the good knowledge of minimization of 1D functions, this above analysis has led to the basic formulation, basic framework, which states that I can minimize a function f of x sitting in an n-dimensional space using a sequence of 1D minimization, and each of these 1D minimization are done in the direction related to Rk. What is Rk? Rk is the residual direction. So now I am going to change the label of the function. F of xk plus alpha rk. Please understand, xk is known, rk is known, only alpha is not known. Alpha is a scalar parameter. So I can relabel this function as g of alpha. So g is a function from R to R, is a scalar valued function of a scalar. The value of g of alpha is equal to xk, f of xk plus alpha rk. So given the n-dimensional minimization of f of x, I just mentioned it, it is reduced to a sequence of 1D minimization problem of g of alpha at xk along the steepest direction rk, which is negative of the gradient, and this I repeated for k is equal to 0, 1, 2, 3, 4. What do you mean by k is equal to 0? That is x0. So what is x0? x0 is a starting point. Those who want to climb mountain, they start somewhere in Nepal. So anybody who wants to minimize a function has to start at some place. In general, a good scientist, a good engineer may not know where the minimum lies, but they know the minimum should be in this box, in this interval. So in general, a good engineer, a good scientist who would have a good working knowledge of where to start my search process. X0 is the initial point from which the search begins. So this is the basis for the resulting minimization. So what is the optimal step length? That's what I am now going to be deriving. I am deriving everything. Nothing is taken for granted. So I have the objective function. I have xk plus 1 is equal to xk plus alpha rk. I have now g of alpha is equal to f of xk plus 1. You remember the previous, from the previous slide. Sorry. You remember from the previous slide, equation at the bottom of the slide 8. So I know xk plus 1 is equal to xk plus alpha. I know what f of x is. So substitute x is equal to this quantity. If you substitute x is equal to this quantity, the function, and simplify, you will get this. That's a homework problem for you to verify. Please understand. It is pointless for me to be able to do the simplification because it is simple algebra. At this master's level, you are all graduate students at this master's level, algebra should not be your headache. Basic understanding the basic conceptual framework must be your focus. So I am going to ask you to verify algebraically. So once you verify this, what is that? F of xk, that's a constant. Rk transpose A Rk. Now please remember, A is SPD, so this is a constant that is greater than 0. That's a quadratic term in alpha. These are the two terms that can be positive or negative, I don't care. This is the linear term in alpha. So what does this function, what does this tell you? The function f of x starting from xk along the direction pk looks like a quadratic in alpha, and that quadratic form is given by this. So this is the shape of the function along the direction pk centered at rk. So that's a quadratic in rk, in alpha. One way to minimize the quadratic in alpha is to be able to compute the gradient. This is a quadratic term, this is a linear term. So the gradient of g of alpha is given by this. In this case, I am computing the gradient equating to 0. So g of alpha is equal to the solution to this equation. If you simplify this, the solution to this equation is given by alpha k is equal to minus rk ax k minus b by rk transpose a rk. The denominator is always positive. From the definition, b minus ax k is rk, so ax k minus b is minus rk, minus minus gets cancelled, so rk transpose rk divided by rk transpose a rk. Rk transpose rk is positive, rk transpose a rk is positive. Therefore, alpha k is always greater than or equal to 0 unless rk is 0. When will RK be 0? If I am at the minimum. So, if I am at the minimum, how do I get to know where I am at the minimum? Alpha becomes very small. If alpha becomes very small, that is a clue that you are nearing the end point, namely the minimizer. So, I decided the direction, I found the value of the step length parameter, all conditioned on the fact when my function f of x to be minimized is a quadratic function, the model problem. Please understand, the concept of a model problem is very fundamental in mathematical analysis. In partial differential equation, a Laplace equation is a model problem. Poisson's equation is another model problem. Wave equation is another model problem. Likewise, for minimization, the quadratic minimization is a model problem. So, I am now going to be defining the complete algorithm, pseudocode. Steepest descent algorithm is also called gradient algorithm. Why is it called gradient algorithm? It uses the knowledge of the gradient to be able to seek the minimum. So, if f of x is equal to x trans 1/2 of x transpose x minus b transpose x plus c, if f of x naught is the initial point given to you, you chose it, nobody gives you, you have to choose it based on your understanding of your own problem. The initial residual r naught is equal to a x naught minus b. If you chose your x naught such that if the initial residual is 0, you had a good luck. You started at the minimum itself. More often than not, it won't be 0. So, for k is equal to 1 comma 2 comma, that means dot 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 dot. So, this is an infinite loop. I am trying to write the infinite do loop for you. Step 1. So, knowing xk, I can compute rk. If I know rk, rk transpose rk divided by rk transpose ark, that is the optimal step length. So, I compute. So, I have a point xk, I compute the optimal step length. I know rk. So, I am going to define the next point to be xk plus alpha k rk, that they iterate. Now, I need to decide whether I want to continue or I stop. I am going to do a test for convergence. What is the test for convergence? The test for convergence is if the norm of the residual vector is very small, exit out of the do loop, otherwise continue. So, this is an infinite do loop. Every infinite do loop must have an exit condition. The exit condition is based on what is called the test of convergence. The test of convergence, as we already saw, can be based on the residual, the length of the residual vector, the length of the residual vector. And if I were to continue to do the residual update. So, these 4 steps are repeated until you exit out of the do loop. So, that is the actual algorithm. It can be very easily coded. So, what is the homework for you? I would like you to be able to code this and to develop a program. Yes, MATLAB has a code, but you should code it yourself. You should code it yourself and compare it with MATLAB to see how good you can code, how good a result you can get out of your own program. That is the idea, that is a challenge. Now, I am going to talk about the performance of this algorithm. So, what are the various things I need to check? I do know locally the function decreases from xk to xk plus 1. So, that is a local behavior. I use the greedy strategy. So, the greedy strategy leads to a very good local behavior. But what am I interested in? I am interested in a global behavior ultimately. What is the global behavior I am looking for? Xk, as k becomes larger and larger, must converge, must move towards x star, the promised land, the minimizer. The minimizer. So, that is what is called analysis of convergence of this method. So, here is the difference. In the direct technique, you develop the algorithm, the mathematics gives you the algorithm. In the iterative algorithm, you use intuition, greedy strategy to design the algorithm. So, locally it works good. I want to be able to make sure globally it works as well. So, much of the challenge in the design of iterative methods is the proof of convergence. the global proof of convergence. Secondly, what is the rate at which it is going towards the minimum? If it goes ever so slowly, we don't like it. We want to converge, we want to prove it converges, and we want to prove it also converges faster. We always require more of ourselves. So that's what the idea is. So I'm now going to talk about further analysis of the gradient algorithm. This is called orthogonality of residuals. What is residual? Residuals are negative of the gradient. Negative of the gradient, they are essentially same except for the sign. So as the method proceeds, I want to be able to understand how the gradient behaves, how the residual behaves. Recall that the residual at xk plus 1 is given by rk plus 1, which is equal to b minus axk plus 1. According to the algorithm, xk plus 1 is equal to xk plus alpha k rk. I substitute this, I simplify. Please remember, b minus axk is rk. So this becomes alpha k a rk subtracted out of rk. So that's a vector. So rk plus 1 is a vector, rk is a vector. I am now going to take the inner product of two vectors. The inner product of two vectors, you substitute rk plus 1 from the above, and simplify, you get a 0. So what does it mean? Rk plus 1 is always perpendicular to rk. Wow, that's interesting. The consecutive such directions are orthogonal. For example, if I go in this direction, this is xk plus 1, the such direction must be orthogonal to that. That's what this says. And that's a good thing to know. Such direction goes orthogonal to each other. What am I interested in? I am ultimately interested in the behavior of the sequence x of k, the potentially infinite sequence given by this algorithm. So I want to ask myself the following question: if I am very patient and I iterate the algorithm, will it ever converge to the true minimum? So that's what's called convergence question. Anybody who is going to deal with iterative algorithms has to worry about convergence. So I'm going to now provide you a framework for the proof of convergence of a class of iterative techniques for minimization of quadratic functions. To many of you this may be new, some of you may already know that. I want to be able to emphasize the proof techniques. That's what the mathematics of data science is all about. So I want to move towards working for the proof of convergence. I already have RK, but to facilitate my argument in the proof, I am now going to define another quantity called the error vector. What is the error vector? It is defined Ek is equal to xk minus x star, which is equal to xk minus A inverse B. So if I define Ek is equal to xk minus A inverse B, if I multiply both sides by A, this is Aek, this becomes Axk minus B, Axk minus B becomes Rk. So now you can readily see Ek is a n vector, Rk is a n vector. So here is Rk, here is Ek, and they are related by a linear transformation A. And what is the related linear transformation? Aek is equal to minus Rk. And A, the matrix A is SPD. So that means this is the one-to-one onto mapping. This is the one-to-one onto mapping. That means Ek has the same information as Rk, Rk has the same information as Ek. So instead of working with Rk, I am now going to work with Ek to consider my proof methodology. But what is the difference between the two? Rk is measurable. What is Rk? B minus xk. I know B, I know A, I know xk. But Ek is not measurable. Why Ek is not measurable? Ek depends on x star and I don't know x star. So even though mathematically Ek is not measurable, the concept of Ek exists. So in analysis, I could use Ek. to do my proof of convergence. So, Ek is useful in proving convergence of the sequence x0, x1, x2, the infinite sequence generated by the algorithm. So, to prove convergence of xk is equal to proving the convergence of Ek to 0. Look at that now. I am transforming one problem to another problem, because I am interested in ultimately making the proof. The proof using Ek, as you will see soon, is a very well established technique, and it is a material I am going to work with Ek or Rk, because they are there is a one-to-one onto mapping between the two, both are equivalent. So, for convenience I am going to pick Ek. So, showing that xk convergent to x star is equal to showing Rk convergence to 0 is also equal to showing Ek convergence to 0. Ek converges to 0. So, to do that, I am going to introduce a new norm called the energy norm of the error vector. So, I now defined Ek. I am going to define the energy in the vector. The energy in the vector is 0 if Ek is 0. If it is not 0, if Ek is not 0, the energy is not 0. So, E of xk is equal to f of xk minus f of x star. So, look at this now. Ek is equal to xk minus x star. The energy in xk is equal to f of xk minus f of x star. So, what is this? This is the value of the function at the point xk, this is the value of the function of the minimum, this is the difference, and this is always greater than or equal to 0, because f of x star is the minimum, that is the lowest point. So, at any other point the value of the function is always above. So, E of xk is a positive quantity. So, I can use this positive quantity and interpret this as energy. You remember that I have introduced the notion of the energy norm. If x is a vector, the energy norm of this is x transpose Ax, where A is a SPD matrix. With this we saw when we introduced the norms of vectors. So, this is called the energy norm. I am now going to show that E of x is the energy norm of E. To do that, I know f of xk, I know f of x star. What is f of x star? X star is A inverse B, f of A inverse B. So, you substitute x star is equal to A inverse B, you substitute f of xk is equal to 1/2 of xk transpose of xk minus B transpose xk plus C. If you substitute this and simplify, please understand there is a homework problem here. You need to verify, you need to believe your instructor, but always with a pinch of salt. You do not agree with him easily, you have to verify to agree with him. So, I do not want you to agree with me too quickly, please verify before you agree. So, this is equal to xk minus x star. So, it can be shown, I want you to simplify, E of xk is equal to 1/2 of xk minus x star times A times, this must be a transpose, sorry, that is an error. But this is equal to Ek, this is equal to Ek, that is equal to Ek transpose A Ek. So, this is equal to 1/2 of the energy norm of A. So, this is always positive unless Ek is 0. So, what is it I have now shown? Let me quickly summarize. I could have worked with Rk, I introduced the notion of Ek. I am going to prove Ek converges to 0 to be able to show convergence. I wanted to relate Ek to some form of a measure, and some form of measure is called the energy norm of Ek. So, now we have shown the energy norm of Ek is equal to the difference between the value of the function at xk to x star. So, how far I am away from the minimum can be computed in one of two ways, either computing x star with xk with x star or f of xk with f of x star. The value of the function gives you another measure. So, this is the measure based on the difference between the value of the function. So, Ek is a positive quantity, it is a measure of how far xk is from x star, and Ek will be 0 only when xk is equal to x star. Therefore, since A is XPD, E of xk is 0 if and only if xi is equal to x star. I am sure everyone should be able to verify this. There is a homework problem simplification. Please do that. So, what is the framework for proof of convergence? I want to evaluate E of xk along the trajectory to prove E of xk is decreasing function of k. Please understand, xk is a vector, E of xk is a scalar. E of xk measures the difference between the present value of the function to the minimum value of the function. We have already seen E of xk is equal to f of xk minus f of x star. So, along the path, if I can show E of xk is decreasing, that means if I go from xk to xk plus 1, xk plus 1 to xk plus 2, my function continues to decrease. That is a theorem in real algebra, in real analysis. E of xk is bounded below by 0. Why is energy? Energy can never be negative. So, E of xk is bounded below by 0. So, if I can prove it is decreasing, a decreasing function that is bounded below must always converge. That is the fundamental principle of convergence. We are going back to again real analysis. That is a fundamental theorem. Let me state the theorem once more. Any function that is bounded below, and if it is decreasing, sooner or later it must converge to that minimum, because at any other point it cannot stay there for too long, because there is a movement towards the direction of the value of the function decreasing. So, since E of xk is bounded below by 0, we want to prove E of xk tends to 0 as k tends to infinity. This framework for the proof of convergence is named as Lyapunov method. Lyapunov is a great Russian mathematician who lived towards the beginning of 20th century, early 1900s. So, it is one of the basic principles of Lyapunov methods. So, what is that we want to do? I want to show E of xk is decreasing along the trajectory. That means, I want to be able to get an expression that relates E of xk to E of xk plus 1. So, E of xk plus 1 is equal to f of xk plus 1 minus f of x star. Xk plus 1 by iterative algorithm is given by this. So, substitute this, simplify. Please understand, and along every way there is a verification, there is a homework problem. Every simplification, when I say simplify, when I say verify, these are all a little local homework problem that you need to be able to see to get the full aha of the method. With B is equal to A inverse x star, it follows that it can be shown by simplifying E of xk plus 1 is equal to beta k times E of xk, where beta k is given by this relation. Please understand, everything depends on the definition of f. What is f? F of x is equal to 1/2 of x transpose ax minus b transpose x plus c. So, this is the value of the function, this is the value of the iterate. You substitute this, simplify, you can express the energy at time k plus 1 is a constant multiple of the energy at time k. So, I have gotten a recursive relation of E of xk energy, and that is very natural, because there is a recursive relation that defines xk. Now, I am trying to define a corresponding induced recurrence on the energy. E of xk plus 1 is equal to beta k times E of xk. The constant beta k that depends on k, it can be shown by simplifying, is given by this. This is the homework problem in each of my classes. It is a very nice exercise in matrix algebra. I want you to do this. I want to emphasize that you have to do this exercise, and you'll have a nice way of verifying this. Please do, please do. Now, let us look at this now. What is the idea now? If I can show beta k is less than 1, if I can show beta k is uniformly less than 1 for all k, what does it mean? E of xk plus 1 is less than because I am multiplying by a number less than 1, EF is less than EF x k. That means that will show. So, if I can show beta k is less than 1, that will imply EF x k to be a decreasing function. A decreasing function that is bounded below must converge. That is the basic idea of the proof. So, I have now transferred all the responsibility of the proof to the parameter bk of the recurrence of the energy function of xk. Proving this is not, proving that beta k is less than 1 needs some other knowledge from analysis. A is SPD, there are n eigenvalues which are positive, lambda 1 is maximum, lambda n is minimum. This is the same A that I am using in my f of x. So, my given f of x is SPD, let lambda 1, lambda n be the eigenvalues. Kantrovich is another Russian mathematician who in the early 1940s was the first one to analyze the convergence of the gradient algorithm. So, in his honor, he for the first one to show that beta k is strictly less than 1. So, in his honor, this result is called Kantrovich inequality. He proved a very general result like this. If A is a matrix, if lambda 1, lambda 2, lambda n are constants greater than or equal to 0, the Kantrovich inequality says for any vector y in Rn, y transpose y whole square divided by y transpose A y, y transpose A inverse y is greater than or equal to 1 minus lambda 1 minus lambda n by divided by lambda 1 plus lambda n. Lambda 1 is the largest eigenvalue, lambda n is the least eigenvalue. So, lambda 1 minus lambda n divided by lambda 1 plus lambda n, that is less than 1. I am squaring that, it is still less than 1. So, this is greater than I am sorry. So, you got this relation, this is called Kantrovich inequality. So, this quantity is less than 1, therefore, this is always positive, we know. But this quantity is exactly the same thing that comes in the previous case. If you change y to Rk transpose Rk, I get Rk transpose A Rk, Rk transpose A inverse Rk. So, Kantrovich proved a general inequality for any n, Rk is the special n, if it is true for any y, it must be true for Rk. So, I am going to invoke this relation, Kantrovich inequality, to show that beta k is equal to 1 minus that is less than this. And how do I show this is less than that? That comes from the Kantrovich inequality. So, by combining the upper bound, by combining the Kantrovich inequality with the expression for beta k, this is the exact expression. This exact expression can be replaced by this inequality by using the Kantrovich inequality. So, what does this say? This essentially tells you lambda 1 minus, so what does this tell you? Lambda 1 minus lambda n divided by lambda 1 plus lambda n whole square. If I get this to the side, this goes to the other side, must be greater than or equal to 1 minus this quantity. With me? 1 minus that quantity is less than this, because we have already shown this one is greater than that. But I can divide the numerator and denominator by lambda n. So, the numerator becomes this, the denominator becomes that. I am now going to define the ratio lambda 1 by lambda n. What is it lambda 1? Lambda 1 is the maximum eigenvalue, lambda n is the minimum eigenvalue. The ratio of the maximum eigenvalue to the minimum eigenvalue is called the condition number. We have introduced the notion of a condition number of a matrix when we did matrix algebra. The condition number of a matrix is always greater than or equal to 1. If it is greater than or equal to 1, when will it be 1? For the identity matrix is equal to 1. Smaller the condition number, better condition the matrix is, larger the condition number, poor condition the matrix is. Therefore, this value beta k is always less than or equal to kappa 2 minus a divided by kappa 2 plus a whole square. Kappa 2 minus a divided by kappa 2 plus a is always a number less than 1, and that is beta. and that is uniformly less than 1. Therefore, beta k for all k is always less than 1. By using Kantorovich inequality. Okay, so the only thing I am not going to prove in this lecture is Kantorovich inequality, but Kantorovich inequality can be proved using certain concepts of convex functions. The Wikipedia, there is a very beautiful proof available. So, I would like to leave it as a reading assignment for you to verify the proof of Kantorovich inequality. So, Kantorovich inequality is the only thing I am not proving, but a very simple elementary proof is available in Wikipedia. So, I would like you to refer to that. Please do go read, understand, and plug it in here so that you can understand the proof of Kantorovich inequality. And also, I have now looking at the application of the condition number of a matrix. Beta k is related to the condition number. Beta k is less than or equal to beta. Please understand, this kappa 2 by kappa, this is independent of k. The left hand side depends on k. So, the beta k is uniformly less than beta, which is less than 1. Therefore, xk plus 1 is less than or equal to beta is the upper bound and beta is an upper bound and beta is less than 1. Therefore, xk plus 1 is less than or equal to beta times E of xk. Beta is less than 1. If I iterate, E of x1 is beta times E of x naught, E of x2 is beta square times E of x naught. In general, I get this relation. E of x naught is the initial energy that based on x naught. Beta k goes to 0 as k tends to infinity. Therefore, E of xk tends to 0 as k tends to infinity. If E of xk tends to 0, xk tends to x star. Therefore, the iterative methods, the iterative method of gradient algorithm or the steepest descent algorithm always converges. This I am going to include as a summary. This is the main theorem of this module. If f of xk is 1/2 of x transpose ax minus b transpose x plus c and A is an SPD matrix, then the gradient algorithm starting at any x naught, any is important, converges to the minimum as k tends to infinity. So, this is a very fundamental result. I am giving you a proof of an iterative algorithm. To many of you, this may be the first time you are looking at a proof like this. It is an ingenious proof by Kantorovich. Kantorovich got Nobel Prize in economics for his applications of linear programming technique to solve economics problems. So, even though he is a mathematician, he was recognized for his contribution to applied mathematics to solve problems in economics. So, Kantorovich, I would like you to go back to Wikipedia, look at some historical perspective of the contributions of Kantorovich, especially to understand the Kantorovich inequality. However, the rate of convergence depends on the value of beta. If beta is very small, convergence is faster. If beta is always less than 1. The closer beta to 1, slower is the speed of convergence. The smaller beta, the value of beta, the closer beta to 0, faster is the rate of convergence. But slower or faster, you and I do not have any control. It depends on kappa. Kappa depends on the ratio of lambda, the maximum eigenvalue to the minimum eigenvalue. Therefore, everything depends on the matrix A. Please remember, in the least square problem, everything depends on the rank of the matrix H. Here also, everything depends on the condition number of the matrix A, which is the matrix of the quadratic function, which is symmetric and positive definite. So, if something does not converge fast, it is not your responsibility, it is the responsibility of the matrix A. So, if the condition number of the matrix A is small, convergence is faster. If the condition number of the matrix is large, the convergence is smaller, slower. Convergence is slower. So, the rate of convergence depends on the condition number. It does not depend on n. What is n? N is the dimension. So, there are lots of indices in here. The f of x is a function from Rn to R. So, n is the dimensionality of the space. K is the iteration number. So, I do not want you to mix k with n. N is fixed. I have a problem of minimization in the n dimensional space. So, the condition number is independent of n. So, that means the theorem holds good for any dimensional problem, but the rate of convergence depends on a single number, which is the property of A, which is the condition number of the matrix A. Now, I am going to compute the estimate of the number of iterations needed. So, we have already shown E of xk by E of x naught is beta to the power of k. Suppose I want beta to the power of k to be equal to epsilon, which is equal to 10 to the power of minus d. What is 10 to the power of minus d? I want the two successive iterations to differ only in d decimals. D could be 3, 5, 7 and so on. That means I have reduced the value of the ratio to 10 to the power of minus d. So, if beta to the power k is 10 to the power of minus d, by solving this we can now express k star is equal to d over log of 10 of 1 over beta. That you can readily see by taking the logarithm of that. So, what is d? D is the accuracy I demand. Beta depends on the matrix A. So, given the accuracy I demand and the properties of the given function, how far I should iterate until I get a result accurate up to d decimals. So, for a given beta, for a given A, beta is given. So, k star iterations will reduce the energy by this quantity. So, I can pre-compute the number of iterations needed. I am now going to talk about the dependence of k star and beta, which is called kappa 2 of A. If kappa 2 is 10, beta is 0.66, I need 40 iterations. If kappa 2 is 1000, beta is 0.996, I need 4030 iterations. If kappa is 10 to the power of 4, beta is 0.996, I need 40,000, more than 40,000 iterations. So, this essentially tries to quantify the dependence of beta and k star for a given d. What is d? So, in these cases I am trying to fix d. D generally is 6 decimal accuracy in single precision arithmetic. We are now going to illustrate an example of the behavior of the gradient algorithm using a simple 2D quadratic function, a quadratic function in 2 dimension. Let me quickly recapitulate before starting the example. We wanted to be able to sequentially minimize a functional. We picked a model problem, quadratic minimization problem. We defined the notion of a descent direction, steepest descent direction. Using a greedy strategy, we converted minimizing a n-dimensional function to minimizing a sequence of 1D functions. The basic idea is I am given an operating point, I am given a direction, how far I can go to get the maximum decrease. That led to the formula for the step length parameter. We stated the algorithm. The algorithm is based on local strategy. In general, algorithm based on local strategy need not lead to global solution. So, we have the burden of the proof that it can globally find the minimizer. Since we took the function to be quadratic, there is a unique minimum exists. So, I want to prove that from wherever I start, I was able to go to the minimum. That led to the concept of proof of convergence. We could have used the residual or the error vector, both are related to each other. We used the error vector. We concocted an energy function of the error, and we showed that energy function, which is a scalar, along the trajectory decreases, and this energy function is bounded below by 0. So, we fell back on a fundamental theorem in real analysis relating to convergence. Any function bounded below and decreasing must converge. That gave you the strength to look for the details of the proof. We invoked the controversy inequality, which we did not prove, but a very intelligent proof is given in Wikipedia, please refer to that. By using the controversy inequality, we were able to show it converged asymptotically. And we also gave a numerical example of the number of iterations that you might need, which is a function of the condition number by using a simple example. So, if I want to get a 6 decimal accurate result, how many iterations I may need to do as a function of beta that we described so far. Now, I am going to give you a further idea about the actual performance of the algorithm using a very simple problem. You can say this example help you to benchmark. So, in algorithm there is a concept called benchmarking the algorithm. Benchmarking means what? I have to certify the performance of the algorithm by working on a numerical problem. That is what is called a benchmark result. So, to do the benchmark result, I am assuming my dimension is 2 because I want to get a good feel. I am going to pick a matrix which is symmetric, which is diagonal, 1 0 0 lambda. The 2 eigenvalues of this are 1 and lambda. I am assuming lambda is 1 greater than or equal to 1. So, f of x is equal to 1/2 of x transpose a x, that is equal to 1/2 of x n square plus lambda 1 x n square, which I can rewrite as this expression. So, you can see this is an expression for the ellipse. So, the contours of this ellipse have major axis, minor axis given by square root of 2 and square root of 2 of lambda. If lambda is large, one of the two axes becomes smaller. If lambda is small, one of the axes becomes larger. I already know where the minimum occurs because this is simply a homogeneous quadratic function. The minimum occurs at 0 0. Please understand, I picked a problem where I know where the minimum is. I am going to start an arbitrary point. I want to be able to test how long does it take to get back to the minimum I already know. This is essentially the way in which mathematicians, algorithm analysts generally certify algorithms, by benchmarking. You pick a problem for which you already know the solution, you apply the algorithm to that particular problem, you follow the track of the algorithm, plot the relevant quantities to demonstrate on this problem where I know the minimum how the convergence takes place, how fast, how slow. So, these examples provide a very good understanding of the numerical behavior of the algorithm. So, the minimum occurs at 0 0, the gradient is Ax, there is no B here, B is 0. So, Ax itself is the residual, negative of the residual, Ax is the gradient which is the negative of the residual. So, I am now going to, I have the algorithm, I already have the algorithm, I am going to start the algorithm at a point x naught lambda 1. So, lambda 1 is the vector, lambda is the lambda is one of the diagonal elements. Why do you want to pick lambda 1 as a initial condition? Why not? It must be able to provide convergence for each lambda. So, I am going to pick the starting point of lambda 1. So, now you can compute my alpha naught. So, I know x naught, I know my x naught is 1 lambda 1, I know my function, I can compute a x naught, that is equal to r, the negative gradient. So, I can compute r naught, which is equal to r naught transpose divided by r naught transpose a r naught, which is essentially 2 over lambda. So, x 1 is equal to x naught plus alpha naught r naught, which is now given by lambda minus 1 divided by lambda plus 1 lambda minus 1. Look at that now. I started lambda 1 in the x 2 x 1 axis, this is lambda, this is 1. Lambda minus 1 is a point below. So, this is minus 1, that is plus 1. So, I am multiplying this by a number less than 1. You can see x. So, this is x naught, x 1 is going to lie on this line, and not a line, it is a multiple of that. So, let me erase this part, that is correct. So, this is x naught, I want to get to x 1, I want to get x 2, I want to get x 3, I want to see how it marches towards 0, which is the minimum. So, continuing this way, so I computed x naught, x 1 from x naught. So, from x 1 I can compute alpha 1, then x 2, then alpha 2, then x 3. So, if I keep continuing this, which I am going to leave it as a homework problem for you to do, you can verify lambda k is given by lambda 1 minus, I am sorry, x k is given by lambda minus 1 divided by lambda plus 1. Please understand, lambda is greater than or equal to 1. So, the numerator is always positive to the power k, and this number is less than 1. K to the power of a number less than 1 shrinks exponentially, and then the x coordinate is always lambda, the y coordinate is minus 1 to the power k. When k is even, it is above the x axis, when k is odd, it is below the x axis. So, you can see it oscillates above and below the x axis, while all along its magnitude keeps shrinking. If the magnitude keeps shrinking, so this is an oscillator behavior. How does this oscillator behavior look like? So, this is x naught, this is x 1, this is x 2, this is x 3, this is x 4, this is x 5. And how do I know actually the direction in which it is moving? We already know r k, r naught, r 1, they are orthogonal to each other. R 1, R 2, they are orthogonal to each other. R 2, R 3, they are orthogonal to each other. We have proven that r k plus 1 is orthogonal to r k. So, if I pick lambda is equal to 4, in k iteration it will be 0.6 to the power k times 4 times 1 minus 1 to the power k. So, the sequence exhibits oscillatory behavior. I want the sequence to move towards 0 0. So, instead of moving steadily monotonically, it moves, but ever so slowly by going up and down, up and down, up and down, up and down. Sorry, sir. By going up and down. So, the magnitude of the scalar that multiplies, that shrinks to 0, the vector itself is above and below. So, it shrinks and moves towards left, and that is what we wanted, because this is x naught, this is x star, it oscillates. So, what does it tell you? This example tells you that this algorithm can exhibit the zigzag behavior, which is not desirable, and this is the reason for slow convergence. You remember we talked about when the kappa is 10 to the power of 4, I need 40,000 iterations. So, if in some problems this algorithm, while it converges asymptotically, in finite time it may not be close to the minimum, it oscillates and takes ever so slow movement towards the minimum. So, theoretically it performs correctly, practically it has an oscillatory behavior, convergence is asymptotic, everything is well understood. I am going to skip this 1D search general case for now. I am now going to take a look back at the sorry sir, I am going to switch off my telephone. So, I am going to look back. The gradient method converges asymptotically for quadratic function, that is we have already proved. In finite time, convergence is not possible with the gradient method. So, what is that it provokes? Does there exist a class of method that can at least theoretically guarantee finite time convergence? See, once you have a good result, we want to get even better. Earlier we did not know whether it will converge. Now I proved convergence, but the convergence is asymptotic. Given that the convergence is asymptotic, given the fact that on some examples it can oscillate, we want to have a better behavior. This better behavior we see can be quantized, can be quantified like this. We would like to have a finite time convergence of sequential algorithm. Is finite time convergence feasible, at least theoretically? The answer is yes. So, as I told you, Kantorowicz proved this convergence in the early to mid 40s. Once Kantorowicz proved this, people started working on this problem and they found that the convergence can be very slow as undesirable. That provoked the new open question, is finite time convergence possible? By end of the 1940s, the early 1950-51, mathematicians have come up with a new class of algorithm called conjugate direction conjugate gradient method, which theoretically can achieve quadratic function, which achieve this goal for quadratic functional. Achieve what goal? If you consider minimizing a model problem in a n dimensional space, I can prove theoretically on an ideal computer in n steps I should be able to converge to the minimum. Please understand, theory precedes practice. So, theoreticians have a lot of leverage. They can assume I am working with a perfect computer. Perfect computer means what? There is no round of error. So, under the assumption that my computer is perfect, the conjugate direction conjugate gradient method provides a framework for iterative minimization that can guarantee performance in no more than n steps on quadratic functions in the n dimensional space.